Okay, so let's welcome our next speaker, Weihong Guo from Case Western Reserve University, and it will be back to segmentation, but with registration at the same time. So simultaneous image segmentation and registration and its applications.
Okay, thank you. I want to thank the organizers for this opportunity. So today I will talk about a task where we try to do image segmentation and registration at the same time. So I will start with some motivations to give some examples about in which situations we care about this kind of problem. Then we will talk about eventually this problem will be solved using a variational model, and we're going to focus on how do we solve the registration segmentation in an alternative way. Okay, so let's start from the first application. So for example, you have two images taken on a different region of interest, but these two regions of interest have a common area. For instance, you have these two images are obviously look similar but slightly different, and they share something in common, like this straight line and this line over here. So if you want to integrate these two images for a bigger picture, or if you want to do image stitching, you want to stitch two images together. And this is used in some cases when you want to take a picture of a big region. So you have to take small pictures in different regions and try to stitch them together. So another application would be like atlas creation. For example, in medical images analysis, sometimes people want to have a standard heart, standard brain. So when people do analysis, they could have some sort of standard to compare with. So they want to create the thing called atlas. Okay, and for example, here I'm showing images of human heart. Okay, so people's hearts are similar, but different people have different size and slightly different shape. So if you want to create a thing called a standard heart, you have to do, for example, this is the whole image, but you're only interested in the heart area. So you want to do segmentation. And also, before you can take average of all different kinds of shapes, you also have to align them. So you need to do registration and segmentation at the same time. So another application would be when people try to do disease progression. Suppose a patient unfortunately get cancer or something, and the doctor wants to do treatment. So after do treatments, they want to see, whether the tumor size is shrinking or increasing. So for instance, on the top row, you see 3 baseline scans at the first time, and the bottom row shows the another later time. So before you can really compare some region of interest, you want to again register them, because even for the same patient, different time when they do scanning, they have different positioning, different angle, or even for the same person, even for example, the lung is breathing, sometimes it's, the size just different because of the nature of the dynamic behavior of certain organs. So you want to do segmentation and registration at the same time before you can compare them. So another application would be breathing cycle artifacts. For instance, here I have so this is a dynamic picture of the lung, and for some time, because we have noise everywhere, sometimes if a image, dynamic sequence of images have an overwhelming amount of noise, you cannot do analysis based on this picture directly. So in this situation, you want to have some other better data to use as a reference before you can do segmentation. So to make sure you can use the data from another patient, at a different time, you want to make sure they are aligned very well. And suppose you're only interested in the lung area, you also have to do segmentation. You don't want to look at the whole body. Okay. So these are the 4 examples. Hopefully, will give you some idea about in which situation do we care about simultaneous segmentation and registration. So mathematically, the notations are, you have 2 images. We call them reference and template. Okay, R means reference, T means template. In this situation, suppose you want to register the template so that it will look like your reference. Okay, so you want to basically, for the registration part, you're looking for a map. Okay, psi such that T composite of psi is close to the reference in some metric. For instance, the easiest one would be the L2, the Frobenius norm. Or in some different modality, if one image is MRI, another image is ultrasound, you probably want to use a metric like mutual information, things like this. And for the segmentation, mathematically, we have seen a lot of good talks on this already. So basically, you want to find a control C to partition omega. So here we just lay out the notations. And so simultaneous segmentation and registration means you want to segment one or two of them. At the same time, you want to also register for them. So obviously, we're going to look for both the transformation, the deformation, and the C at the same time. So because this is a variational workshop, so we're going to solve this problem by setting up a mini optimization problem where the terms are based on variation. And so now depending on, we have seen 4 different application examples earlier. So depending on the application, you probably want, sometimes you probably want to segment both images at the same time. Sometimes you only want to segment one of them. Sometimes you only want to register the reference, or sometimes the other way around. So it all depends on what application. So I'm going to start with some literature review. So let's start with a 2001 work where they were targeting on segmenting 2 images at the same time. So the model looks like this. So we're all familiar with yesterday, Wei Zhu gave a talk about the segmentation. So the notations were probably this note. All these terms look familiar to you already. So basically, you want to segment both pictures, okay? And the contour for the first one is called a C. The contour for the other one is called a C hat, okay? So for the first image, you want to make sure the intensity inside the C is close to one intensity, and outside the contour C is close to another intensity V. Similarly, for the second image, you have something similar. You want to look for a C hat such that inside the C hat is close to a value, say U hat, and outside of the C hat is close to another intensity. So this is a straightforward way of doing 2 segmentation on 2 images at the same time. And what is different from the doing individual segmentation is that they try to connect the 2 contours using a rigid deformation. So they assume that the 2 contours have a rigid relation, like rotation plus a shifting. So basically, they want to solve this and minimize this energy function with respect to the contour C and also this, the angle, the rotation, the shifting. Okay, so this was one of the very early work on simultaneous segmentation and registration. So, so over here, the rigid registrations that we have heard about, earlier talks mentioning about deformable, deformorphism, deformable registration. So this is a rigid one. For some applications, the thing called a deformable registration is more reasonable. For instance, the heart or the lungs, there are soft tissues. They're not always just doing rigid rotation or shifting, right? Actually, they're stretching and shrinking. So you want to have deformable registration. So so the notation is like we saw this notation earlier, but here I would want to emphasize that we're gonna sort of try to figure out this deformation by simply figuring out the displacement, because this is a pointwise deformation. So it will be equivalent if I just figure out the displacement at each pixel. And this can be done by setting up a optimization problem. You want to minimize this with some distance metric. And if you solve this directly, obviously it's an E-opposed problem, so you want to propose some regularity. So one of the very nice regularity is based on linear elasticity. So basically, you want to imagine that the object of interest is the image of some object that is very easy to deform, like something like the headband or like the stuffed animal. You can stretch them, you can press on them. So things like this, or soft tissues like heart or brain. So you want to make sure that you sometimes at different locations you have different kinds of deformation. So this is one example of the. So mathematically, It's representing how do we describe, how do we add a regularity to make sure that your deformation is satisfies certain linear elasticity. So here is the mass. So they want to, this is the regularity they add on. So in this regularity is based on, it's the thing called the strain energy. Okay, the strain energy is defined as the sum of the square of the trace and the trace of the omega squared. The omega is equal to this. Remember, the u is the displacement, and this is simply the gradient of the displacement, which is actually a matrix because u is a vector. So this will be a matrix and plus the transpose of the matrix. So by minimizing this kind of energy, strain energy, you will be sure that your deformation satisfy linear elasticity. Unfortunately, this kind of energy function will lead to a very small, tiny deformation. Okay, you cannot deform very much. But in some applications, you do want to have large deformation. So one way to allow large deformation is to add another term in the in this EU term. Okay, so this was what was seen earlier. And if you add another term over here, you're going to end up with a Lagrangian strain tensor. And if you minimize respect to this, that this new regularity is going to lead to a larger deformation. And so regularized registration cost would be, you use this is a very typical optimization, variational based image segmentation. So you want to, this is a regular fidelity term. You want to deform, you want to register this template so that it's close to the R. So here, just as a demonstration, we used L2 for Frobenius norm. But if you have different modality, you can simply replace this by some other things like mutual formation if they belong to different modality. And and this is the regular. This is the regularity we mentioned earlier, Lagrangian strain energy. And I would like to call your attention because later you're gonna see different work. It's kind of difficult to see the difference. So over here we are starting from the template. We register the template so that it's close to the reference. Okay, I know you might have a concern about how can you go back? Is it reversible? In this case, we are talking about the for some applications like the disease progression. So you have the data at the first time period, and now you have another data at the second time period. You want to see, comparing to the first time, is the second one, is the tumor smaller or larger? That's what you really care. So you want to know, after I get the data at the second time period, how do I compare with the first one? Okay, so we're going to use the data you learned, you collected at the second time point to be your template, and you register your template data to the reference, which is the one you collect at the time one. So you want to see the difference. So to go to, if it's diffeomorphism or not, might not be a very concerned issue over here. Okay. So we're going to adopt this kind of model for our registration part. Remember, we have simultaneous segmentation and registration. So for another related work is by Gayadar and Vesi on 2011. See, the idea is that they do the segmentation on the reference. Okay, so same idea. So they want to segment this R, which is the reference image, so that it's close to C1 if it's inside a region, and it's close to another constant if it's outside a region. And the inside or outside is determined. It's not like the typical Chen-Vesi model where you have the h phi 0 of x. But instead, this phi 0, which is actually a level set function coming from the T image, the template image. So you are registering the template image and use that template image to tell you where the boundary is. Okay. So you have h phi of 0, x minus u. Remember, when it's from t to r, we used x plus u. So from r to t is x minus u. Okay. So you have this. So you are actually only doing segmentation on the reference, and you're registering from from the t to r. Okay. And over here we highlight this region. If you still remember, in this strain energy with the Lagrangian strain energy, we had terms like this. We had terms like a trace of this kind of thing, which is based on the gradient of U. But it's kind of difficult to solve when you have gradient U showing up everywhere. So they introduced a splitting. So they introduced a auxiliary variable to split the terms. So as you could imagine, when your image R is D dimension, then you're gonna have D square you're gonna need D square of the auxiliary variables, okay? And each one of these variables is gonna have the same size with your original image, okay? So computationally, it's a little bit burden over here. And another newer work is about, this we focus only on the registration part, the irregularity, because the fidelity will be the same. So the regularity is based on, this is what we have seen earlier, the Lagrangian strain, the strain term. And they added another term where it's determined as, which is called a determinant of f minus 1. So this is to make sure that when the object is deforming, the volume is not changing. So they want to preserve volume. And also they, in this, so they are also doing, this is a typical this is a typical fidelity. This is a regularity. They introduce auxiliary variable. And another slightly different thing is that they use, instead of using just the gradient of the t, they use the weighted TV in the front. Okay, so weighted TV was a very popular tool when people want to preserve edges better than other regions. And they also use this splitting method. They introduce another set of variables to make the computation simpler. All right, so the next we talked about registration. We're going to use this thing called Lagrangian elastic, Lagrangian strain energy, minimize that Lagrangian strain energy to deform our registration. So if you are not familiar with this, strain energy, it's like this. So suppose this is the elastic band. You can stretch it, and you can do anything you want. But when you want to minimize that strain energy, it means that after you release this, you will return to the equilibrium. That's what it's pretty much saying. So you could do a deformation to it, deformable registration to it, but with that regularity, you want to make sure that it has some regularity so that it can return to the equilibrium, things like this. So another task we're gonna have in this simultaneous segmentation registration is the segmentation. So for the segmentation, we reviewed some of this already, so I probably can skip some of this real quick. But notation-wise, it's like you have a U0 image, you want to find a contour C to separate the inside outside. And the level set formulation was some very popular tool, for decades. And the main reason was that the level set is able to handle topology change very flexibly, but unfortunately, this kind of Chen-Vesey model, which is based on is a piecewise constant sort of approximation to Montfaucon model, is not convex when you use a Heaviside function. So then later on, Tony Chen and his collaborators try to simplify it into a problem like instead of using, because the main reason for people to use Heaviside function is that we just want to separate inside from outside, 0 or 1, right? So why don't you just define the whole Heaviside, just replace the whole H of phi by something like close to binary, but binary is again not convex for domain-wise, so they relax it to make sure phi is between 0 and 1, okay? And later, Bresson, they replace this TV by weighted TV, something you have seen earlier, just to make sure that the boundaries are kept better, more sharp boundaries. So we're going to adopt this as well, but slightly different with what was seen in the literature is that, remember, we're going to merge the two tasks together. So we're gonna do this. We're gonna do this segmentation on the registered template. Okay. So instead of applying the segmentation only on the template, we're gonna start from the template and do the registration to deform it, and then do segmentation on it. Okay. So if you are confused about this kind of complicated procedure, keep that disease progress in mind. Okay. So T is the data you get at the second time. So you want to deform it, and you also want to segment the tumor out of it, and to compare with the tumor size at the first time. Okay, so you want to do start with the T, do the registration, and segment it. All right, so we talked about the registration and the segmentation. Now let's put all of these terms together. It's a very typical variational model. So this is the closeness in between the registered T and the reference, and this is the regularity on the on this displacement field. Remember the strain energy, and this is a term to make sure that the phi over here takes care of this segmentation. Phi is going to be between 0 and 1. And inside the certain region is phi is going to be 0, close to 0. Outside the contour is phi is going to be close to 1. Okay, so being close to 0 or being close to 1 will tell you if it's inside the object or outside the object. And so the computation of this will be done based on a alternative optimization, because we have the U, which is the displacement field, and also this phi, which is a segmentation function. So we're gonna compute them in an alternative way. So this displacement subproblem, we're gonna use numerical PDE to solve for it. Okay. Remember earlier we reviewed some literature work where they introduced auxiliary variables and do splitting on it, and we thought that is kind of a little bit burden if we have a high dimensional to handle, because we're going to introduce a d square. If your dimension is d, then you're going to introduce d squares of extra variables, which is a little bit too much for us, because as you could see, the problem itself is kind of complicated already, so we don't want to introduce too many more terms. And so we're going to go back to the very raw way of solving for this. So take the Euler-Lagrangian and solve for it using typical differential equation, the PDE method. And we try to make it as explicit as possible. Whenever we have linear terms, we're going to move to the left, and it's going to be a semi-implicit approach. For the other one, for this phi subproblem, we are able to solve for it solving a minimization problem directly. We don't have to compute the Euler-Lagrangian. So all of these subproblems eventually will have some sort of closed form. We're going to use the Fourier and the inverse Fourier to solve for this subproblem, and for this subproblem, they all have closed form solutions. So let's look for details. So if you collect all the terms that contains U. You have U here, and U here. For this U, we want to mention that this term is a super nonlinear. Okay, we do not want to mess up with this super nonlinear term at all. So during the iteration, we're gonna take the very recent iteration for the U, and then we're not gonna take the keep this U into the computation for the. So you're gonna do this kind of find the Euler-Lagrangian and discretize things, using periodic boundary condition, and a lot of these terms will be able to be computed by convolution. Okay, a lot of us are experts in the area, so so a lot of these terms can basically just burn down into convolution with all kinds of kernels like forward, backward, or central, and eventually this structure will be, as I said earlier, if you have some sort of linear terms, you're going to move to the left. For nonlinear terms, you leave on the right. So you will make it semi-implicit, and hopefully we're going to make the step size a little bit bigger. And if you're familiar with this kind of PDE, eventually you're going to have a BCCB structure, okay, blockwise circular block. So and then all of these sub-problems be able to be solved using Fourier transform, okay, blockwise Fourier transform, then inverse Fourier transform. Okay, so it's block circulant. Okay, so we don't have to worry too much about this. It looks very overwhelming just because of the nature of the problem, but mathematically the structure is very simple. For this U, the displacement subproblem, we just derive the Euler-Lagrange and discretize all these differential operators using using periodic boundary condition, and the structure eventually will be very simple. So you can solve for them doing blockwise. So the other subproblem is regarding the segmentation. So we want to minimize this energy function with this constraint. So phi is the between 0 and 1. And for this, based on the work by Bresson in the 2006, we can absorb this constraint into by adding a extra term into our function, which looks like this. Then you'll be able to solve this problem. If you think this is too difficult to solve directly, then you could introduce another variable to split it. Okay, so you can introduce another variable to split this phi. Then you're gonna change the regional minimization problem. Only has one variable into two subproblems, and each one of this subproblem can be solved much easier. In particular, this one you can solve it by using shrinkage. And this one you have a closed form as well. Okay, by using minimum maximum operator, you'll be able to find a closed form solution. All right, so eventually our the update rules would be you have the deformation, you have the two variables coming from the segmentation. So you put everything together, it will look like this. Okay, again, looks overwhelming, but the structure is very simple. In particular, every one of these on the right-hand side are very computational friendly. So Fourier, inverse, closed form, things like this. And one thing I have to mention is that we do need to do interpolation somewhere, because remember, we need to apply the t of the u, right? So your x plus u might fall onto somewhere which are not on the grids, so we have to do interpolation. All right, so we stop this using very typical stopping criteria. So you want to make sure that the relative errors are small enough in adjacent steps. So let me show you some of the results. So this is a very simple result that shows you how do we deform a square into a long, slim rectangle. So you can see that the deformation is quite big. And this is the deformed grid. Okay, you start from this, I'm sorry, it's not a square, but it's a chunky white rectangle, and you want to deform to a pretty slim, tall rectangle. And here we have a picture of if I can show you. So we're going to deform this ellipse into a cat. So the idea is that this is a template. We want to segment this template and deform it so that it will look like this reference. So the tail is kind of a very small detail, so it takes time to recover the tail. And this is the eventual deformed grid. So you started from this regular square grid, then you deform it so that it's comparable to the cat. And this is a set of brain images. So again, this is your template, this is your reference. You want to compare these two after you align them. So it's just because this is a brain, so it's not like so much crazy deformation as lungs. So the brain does not really deform that much. So the deformation you see is very small. And we only did two-phase segmentation. So if you're super worried about the four-phase segmentation, then you could change this our segmentation part into the four-phase segmentation. All right, so this is the some of the lung pictures you have seen earlier. So we had a reference lung and it's a template lung. So we want to compare these two before, after you align them. Because if you do a direct difference, like you take the reference minus the template, it does not really make sense to you. Because remember, the lung is moving. This might be a lung you take at a different time than this. So it's not reasonable to compare them directly. So this is the difference after you align them, okay, which is the difference is much smaller. So this is a sagittal view, another view of a lung, and it's the same idea. And this is the phi. Remember, we use this phi of phi to do the segmentation. So the phi technically should be between 0 and 1. Okay. So numerically, you're going to get something in between 0 and 1. So we can do a simple threshold. If it's bigger than half, it's one phase. If it's less than half, the other phase. Sometimes the computation, this threshold is not really a big deal. So because you will see that in your result, your phi is either very close to 0 or either very close to 1. Okay, so somewhere in between, any sort of threshold will be okay. It's not that sensitive if the computation is done very correctly. Okay, so this is one of this the atlas creation example I showed you earlier. So you have two lungs. It's a different, it's a vertical view. So you have a sagittal, vertical, just different cutting. Sometimes vertical cutting, sometimes this way, sometimes this way. So it's different view. So you want to compare them. So you want to register this before you do comparison. And here is the determinant of the psi. This is the one in some of the models. They put the extra term over there to see if it's close to 1. If it's close to 1, that means the volume is not changed much. Okay, so you can see, even though it did not put any constraint about restricting the determinant to be close to 1, eventually in the result is still very close to 1. Okay, because we have a lot of terms like registration, segmentation, try to control them implicitly. So it's not going too crazy. Okay, I guess I speak too fast. Conclusion. So we presented a work where we try to do segmentation and registration at the same time. So the motivation behind is that for certain applications, both of them have to be handled at the same time. And that one issue is that some people might be concerned, why don't you do in a sequence? Why don't you register them first, then you do segmentation? So it's pretty natural. So I'm not saying that it's not working. It's just that for some problems, it's better to do simultaneous segmentation and registration because you can hopefully reduce the error coming from each one of them. Okay. And of course, if you're able to handle each one of them perfectly, it's probably not much accumulating errors, but you never know, it might be some error here and there. And another different perspective is that when you combine the two tasks together, hopefully they're helping each other. In particular, if now the images are so reliable, if now these things are accurate enough, they probably can help each other. For instance, in for segmentation, sometimes it's very difficult if part of the information is missing, like in ultrasound. When they take ultrasound of a human heart, there's always one part of the intensity is always missing. So you have to use some prior shape to guide you to fill in the missing intensity information. So this kind of missing intensity information could be obtained from, because there's no if there's no reliable atlas and there's no reliable shape for you to follow through, you probably have to try to figure out the shape once you do your task. So it's like a simultaneous shape prior searching and this kind of a shape prior guided segmentation registration. So we are trying to combine things together. So hopefully you do not require too much prior information. So you pretty much use whatever you have to get the things you want. And so this is a work done by my former PhD student, and he has a lot of interest about the applications on medical images. But as you could see earlier at the very beginning, that it's not always just medical images. It could be used to see in things like biology and also like material science. When you have images taken at a different time, you can always use things like this. And as you could see, the segmentation right now, we only have done just two-phase, foreground, background, but we can extend this to multi-phase segmentation. And also, how do we do dynamic 3D or even 4D? That's something we could explore. Okay, so I would like to thank my former PhD student Thomas, who has done a lot of work on this, and a grant. So here are some references if you are interested. Okay, thank you.
Are there any questions?
I was curious in these applications, you usually assume that the measurements are coming from the same modalities. And in medical imaging, sometimes you get two different modalities, like CT and PET.
Yes.
Is it possible to apply these methods when you have two different kinds of measurements?
Yes, you could change the fidelity term. Right now, the fidelity, just as idea of demonstration, we use the Frobenius one, but you could use mutual information. Like mutual information would be something, or KL divergence, something that is based on distribution. When you cannot compare the intensity directly, you could compare the distribution. Yes?
If I thought correctly, you are segmenting, let's say, the template image and transfer it to the moving image. So would it make sense in some cases to do the segmentation of both images and have a term that ensures that they are mutually in agreement?
Yes, yes, it does make sense. Yeah, as I mentioned earlier, depending on a particular application, you might want to change your model a little bit. I guess the way I presented the energy was having the example of the disease progression in mind. When you have, suppose the reference is the day 1 data, and the template is the day 2. For example, somebody unfortunately got cancer, right? So what they really care is my cancer tumor get smaller or larger? So they want to do comparison. So they want to register the day 2 data to the day 1. But for other applications, you might want to register, segment both and do alignment. So it will be mathematically more decent, especially the diffeomorphism things. You want to make sure your registration can reverse, things like that. Yeah, I guess here we're just trying to promote the idea of doing two things at the same time, but there's a lot of things you could change, make it mathematically more decent, I guess. Yeah.
How important is the second order in EU?
It turns out to be very important. You mean the gradient U times gradient U transpose?
This is like second order in Taylor series.
Yeah, it turns out to be that's the term that can make sure your deformation is big. If you do not have that term, the deformation can only be very small. As the example I showed you earlier, we changed the ellipse to a cat, which involves a very big deformation. So without that term, you cannot do that. Yeah, it's a small, very small deformation.
And also, we use Lamé coefficient, which assume isotropic. Generally, you have like 81 coefficients, and by symmetry and isotropic assumption, you throw everything but these two.
That is the expression of the deformation gradient, the one that she could see.
You mean the weighted TV term or this strain energy term? Strain energy, right?
Yes.
Yeah.
So you have a tensor between the stress and the strain, right? And so this is like 81 coefficient, 9 by 9. And you assume, in order to get to the Lamech coefficient, you assume isotropic deformation.
I don't think I get your question. So we are not assuming it's any 9 by 9. So if the U is a pixel by pixel information. So so if the given image is
Locally isotropic. So this is the assumption.
I'm not sure it's something. Yeah, we can talk. I'm not sure it's in there.
Do you compare with the non-periodic boundary condition?
Yeah, that's a good question. If it's non-periodic, we can use some other boundary condition than like a zero boundary condition. Then we just have to change the structure. So I guess right now we just want to appreciate the convenience of Fourier and the inverse Fourier. Yeah, but if it's something, because a lot of the deformation happens inside, so it's it's true that the boundary condition is going to affect eventually. But I guess right now we are enjoying the convenience of Fourier and inverse Fourier. But if it's different, we have different PDE to solve. Yeah.
The minimization with U between 0 and 1, so that's essentially a min cut problem. So
U is the phi is between 0 and 1.
the
U
segmentation with the U between 0 and 1, that's essentially a min cut. So you can solve it much faster by the standard graph cut or the continuous min cut mark flow.
Yes, exactly. Yeah, Professor Tai.
So there was formulation to show that's exactly the due of the Marx flow and it's a min cut.
Yeah, we can talk offline.
You raise, right.
You said your W, the energy density, is not quasi-convex. What's the meaning of quasi-convex?
Oh, it's like if you sketch the graph, if you cut a horizontal line and the inverse is convex.
It's not.
If you have a V-shaped function, then you cut a line. Or if you have a W thing, if you cut a line, then the inverse of that is not a.
So it's not the meaning in the sense of calculus variation, rather than in the convex analysis.
It's the same thing.
No.
Yeah.
No. Actually, the energy that you use is the design which is not fully convex.
Yeah, the whole energy is not convex.
Yes, the lower semi-convex envelope is the so-called quasi-convex envelope. Well, in the sense of Mori, though.
Yeah.
It's not that.
Oh no, I thought you said the quasi. No, it's
But the lower semi-convex envelope is not the convex envelope, though.
No.
So have you calculated the convex envelope?
No, we didn't. We just solve for it directly. Yeah. It's technically we might get stuck somewhere, but fortunately we haven't have any problem yet. But it's theoretically is not a convex model. You could end up with a get stuck in local minimum, but fortunately we haven't seen that happened yet.
An assumption of your model is that you find the global minimum on this, which is not convex function. By using the alternating minimization, it's separately convex. By using the alternating minimization, you are not guaranteed anyway to get to global minimization. How do you check this? Because you solve then the Euler-Lagrange. Do you have a check? Do you make a check?
Well, so far, because the nature is not convex anyway, so we could technically get stuck somewhere. So the best thing we could do is to keep track of the energy function. To keep track of because we're minimizing a energy functional, so we can keep track of the energy functional across time. So, that's.
And you get in maybe in a local minimum.
Yeah, technically you could, yes. Yeah. Because that's but as I said earlier, we haven't seen that happen. Yeah, because results look reasonable.
So no, there is
so you're right. We could technically bump to a problem of having stuck in a local minima because it's not convex, right?
Thank you.
Thank you.
Can I just ask one Could you go back to one slide where you had lung segmentation?
Sure. This one?
No, that's not lung. Okay, here. I'm just kind of curious. So you have those red lines on the right-hand side, which I guess correspond to this. Are they perfectly registered? There is no some kind of. You see what I'm trying to say? I don't see any motion for those vertical lines. And
so this is the because our segmentation we did not do the region of interest selection yet. It's completely rely on the foreground background. So this the vertical thing you see, they just unfortunately they share the same intensity, close intensity.
Exactly the same locations.
We are not discriminating by location. So we rely on the phi, the level set. Well, sort of phi. It's not eventually not level set, but.
I mean, why there is no motion there in the deformation grid? That's what I'm saying. Like if.
Oh, you mean this one, or you mean this one?
Yeah.
Oh, this is not the deformation. Deformation should be read from here.
Right, and I don't see any deformation, so I'm kind of wondering, is that the same? Like, I'm not quite sure I understand how to interpret the deformation grid with those. Your segment is quite complicated with those artifacts on the right-hand side.
Yeah, you could basically ignore this because what you see on the red curve is the segmentation of the register one, and this guy's the intensity happens to be the same, close to this one. They belong to the same phase.
But then on the deformation grid, it seems like there was some deformation in the center where the lung is. But on the right-hand side, I don't see any deformation. So
oh, you shouldn't, because that's the background.
Why do I see red lines then?
Oh, that's just you start from everywhere you have a grid. You start from a regular horizontal, vertical, and then you deform that. Even there's no deformation, you still have the regular horizontal, vertical. Just like a tector, you start from a discretization, like for digital images, it's always based on discretization. So you're starting from drawing the regular, horizontal, vertical grids.
Maybe I'm misinterpreting.
Yeah, sort
They are
of.
segmented, but they don't move. So there's no
That's what I was kind of trying to.
The red one does not mean it's moving. So to see if it's moving or not, you see things like this. It's not like a regular horizontal vertical anymore. That means there's deformation happened over there. Over here, if you zoom in, this is just a regular horizontal vertical. Means nothing happened.
Okay.
Yeah, it's yeah.
Are these deformation what you expect is kind of very strong compression at the bottom and not much less at the rest of the lungs, or is it something that you
very strong compression at the
yeah,
bottom?
you see the deformation grid is very compressed at the bottom of the lung.
Yeah, I guess it's
Later, is it
yeah, I guess
small estimate?
it's like you have a lung, right? Lung goes like this.
Yeah,
So-
but does that compress
Yeah,
just like that?
yeah, it's like that. Where you start from, like where you have air in is bigger, right? When you have air out, is smaller.
Well, it's not everywhere.
Well, it's sort of regular actually. You see a kind of regular movement. It's not like going crazy, so different everywhere. They still have some sort of continuity, like gracefully deformed.
Deeper.